This video is over Objective 17.2. Let's start with a little bit of vocab. The vertical line test is a relation, is only a function if a vertical line drawn anywhere on the graph only touches one point on the graph. We will use the vertical line test in a little bit to determine if some things are functions. But go ahead and pause the video and write down that video now. One thing that you should be well versed in by now in algebra is plotting points. And so that's what our first example tells us what to do. It says graph the following relations and use a vertical line test to determine if they are functions. So first let's graph our points. Go ahead and pause the video, plot your points, and then hit play when you're ready to check. For example 1 on our first graph, this is where you should have your points plotted. Now let's utilize the vertical line test to see if this is a function. Looking at our graph, the only place that looks like would present a problem is right here. Notice if I draw a vertical line through x equals -3, it touches 2 of the points on the graph. That tells us that this relation is not a function because any vertical line can only touch the graph at one point on the graph. The reason that this is the case is because -3, the vertical line through it, represents an input of -3. Two different points resulting on that vertical line means that it has two different outputs, which means this is not a function. Go ahead and pause the video again and plot the points on the second graph. Notice on this graph there's only 4 points. Take a look at it and see, is there anywhere we could draw a vertical line that would result in hitting more than one point? Well, there's only 4 vertical lines that we could draw that would hit any points on the graph. And none of those vertical lines are going to hit more than one point, which means yes, this relation is a function. All right, example 2. Complete the table and mapping diagram for the following function, then graph the function. We actually did this in lesson 1, at least the table and the mapping diagram part. So we're going to try it again, and then we're going to add a couple of new components. So remember when we are completing a table, we are going to plug each x value into our equation. So our equation is f of x equals 3x minus 1. So when x is -2, I'm going to plug -2 in for x. It's going to give me -6 minus 1, which is -7. I'm going to do the same for the rest of my numbers. Go ahead and finish completing this table, and then press play when you're ready to check yourself. If you don't remember how to complete a table, please refer to the video for 17.1. Your table for this function should be completed as shown. After completing our table, we can complete our mapping diagram. I like to put my numbers in numerical order. So for my inputs, I'm going to start with -2, and then -1, 0, 1, and 2. I'm also going to put my outputs in numerical order. -7, -4, -1, 2, and 5. And then remember, we just map the output or the input to the correct output. -2 goes to -7, -1 to -4, 0 to -1, 1 to 2, and 2 to 5. These are kind of boring mapping diagrams. Sometimes different inputs go to different outputs. The outputs have multiple inputs, so on and so forth. All right, so now we are going to graph the points from our table onto our graph. So once again, you have the table completed. Pause your video, and I want you to complete the table, or take the table and graph it onto the graph, and then hit play to check your work. Notice that the points that we plotted form a line. Because this is a function given in function notation, we're not just plotting the points, we're actually graphing the function. And so go ahead and connect those points to form the line. Remember, lines continue in both directions. Lastly, we're going to complete a relation. A relation is just a set of points, and all we're doing here is putting in the outputs for each input, which we already found. So -2 has an output of -7, -1 has an output of -4, 0, -1, 1, 2, and 2, 5. And those are 4 representations of functions. We have the table, the mapping diagram, the graph, and the relation. There's other representations as well, but we'll stick with these for now. For this last example, we're asked to state the domain and range for each graph and then tell if the graph is a function. So this is going to be a little tricky because it's something we haven't learned yet. So domain, as we stated in our vocab section, is the set of input values, or the X values. So if you look back at lesson 1, that's where you'll see that definition. So if we take a look at this first question, question A, we're looking at this graph, and we're looking at our set of X values. And so notice here we have just single points graphed around. So we have a point here, point here. Okay, so we are going to list the X values of all of our points, since there's only 5 points. So what we're going to do is I'm going to do this in numerical order. So I'm going to start on the far left. So the smallest X value that's included in our domain is the one that comes from this point right here, which would be -3. And then we move to the right. We have -2, 1, and 4. Those are the X values in our domain. We're going to do the exact same thing with our range, but we're going to start from the bottom and work our way up. So our smallest Y value is -4, and then -2, 0, 3, and 5. So next, we're asked to answer the question, is this a function? So when you go back to your vertical line test, is there anywhere that we could draw a vertical line that's going to touch this graph more than once? Well, right here at x equals 1, that vertical line hits 2 different points, which means no, this is not a function. Let's take a little look at B. Now this one's different because this isn't just a set of points. These are lines these are points being connected by lines. And so when we write the X values for this, we can see that it's not a single point here and a single point here. It's every single point in between. And then every single point between here and here. So we have points all the way from -3 to 3. And if we draw it this way, we can see the same thing. It's continuous, okay? And so what we're going to do is we're going to write an and inequality to show the x's between the values of -3 and +3. So think back. How do we write an and inequality? How do we say x is between two things? This is what that's going to look like. It's between -3 and 3. Okay? Now, I put equal signs on both of those symbols because there are points at -3 and 3. So pay close attention to when we're going to have equal signs or not, okay? All right, so now we're going to do the same thing for our y. So if you're kind of questioning what we just did, watch this one. So y goes all the way from here to here and every point in between. All right? So y is between. So notice I'm going to put both of those symbols are going to be facing the same direction. Y is between -4 and +3. Okay? All right, so now it asks, is this a function? Well, if I draw a vertical line right here, look what happens. It touches twice. So if it's touching twice, that means that no, this is not a function. Okay, so let's try that again. This one's going to be similar. Okay, our domain. So let's start with our domain. Our x values goes from here all the way across, and it keeps on going to the right forever and ever and ever. Well, how do we say that something keeps going? Like, if it doesn't stop, it's going to infinity. So that arrow represents this going to infinity. So x is between -4 and infinity. So now we're asking ourselves, should we put equal signs here? If you look back at our original drawing, there's an open circle at x equals -4. That means there's not actually a point there. It gets really, really close. It could get to -3.9999, but it's never going to touch -4. So I'm not going to put an equal sign there because of that open circle. This arrow going to the right implies that it keeps going to infinity. I'm not going to put an equal sign there either because we don't use equal signs with infinity because infinity is more of a concept than an actual number. Okay, so now let's move on to our y values. Our lowest y values are going to be right here at 1, and they go up to 3 right here, but they also keep going up forever and ever on this side. So our y values are going to be between 1 and infinity. Didn't mean to make that equal sign there. Now, which one of these would need an equal sign? Well, there are values at 1, so I can put an equal sign on that one. But remember, we don't put equal signs with infinities. So then we're going to ask ourselves, is there anywhere that a vertical line is going to touch our graph more than once? And I'm not seeing any trouble areas here, so I think it's safe to say that this is a function.